I'm going to try to use this instead of the laser pointer. Yeah, so this is some kind of like an overview talk, maybe based on several papers, together with Fernando, Omar, Christoph, David, and Marco. Some of them are here. Okay, so let me start with a few like motivational slides, which maybe for this audience I can go over rather quickly. Okay, so what I want to talk about here is entropy, is quantum entropy, right? This is for Neumann entropy as we know it. However, I would not like to look at a single system, but at multipartite systems. And if we look at multipartite quantum systems, and then we take the reduced states, okay? So if these reduced states overlap, here, for example, the blue one, AB, and the orange one, right, BDE, then of course the marginals, the density matrices, they don't commute. Okay, so we have this non-commutativity, and that's why it becomes mathematically pretty challenging to study the entropy function. And then basically all we know is this strong sub-additivity from the 70s, right? So this is on a tripartite system, ABC, and then if we look at the sum of the entropies on AB and BC, then this is never smaller than the entropy of the whole system plus the entropy of the intersection of these two subsystems. Okay, and so this is, I don't have to tell you that, right? It's a very essential tool in any quantum information science that you pick, basically. And I would argue here, I would want to argue that this is basically because it gives us a constraint on the multipartite entanglement structure of quantum states, right? Good. Now, of course, we can ask, like, how do we actually prove this? And the way one proves this is using so-called matrix trace inequalities, right? And so I have here, first example is this Baker-Campbell-Hausdorff formula. Here there's actually no trace. But here I just want to show that if you do like elementary operations with matrices, then things that you know would hold for numbers or probability vectors, they don't hold anymore in this non-commutative setting. So for example, if you take the exp of h1 times the exp of h2, it's not just the same as the exponential of h1 plus h2, but you have this long sequence of commutators, right? Like in this Baker-Campbell-Hausdorff formula. Now, the hope is, of course, that if we put a trace around it, it becomes a scalar quantity again, and then maybe we would have these normal identities that we have for numbers. Unfortunately, this isn't true either, but one can prove nice things like the Golden-Thompson inequality. Okay, so once you put a trace around these two expressions, you know you get this inequality. Okay, so you can upper bound the exp of h1 plus h2 with the single terms, basically. Now, the problem with this is all very nice, matrix analysis is very nice, but if we want to look at multipartite quantum systems, basically what we need is we need a multivariate trace inequalities. Okay, we need matrix trace inequalities that hold for more than two matrices. And here, the landscape is very dry, let's say. There are only very few results available. And actually, for a long time, the only available result was exactly the result that allowed to prove a strong sub-additivity of quantum entropy, okay? So this is the so-called Lieb's triple matrix inequality. And here, just instead of these two matrices, if you want to upper bound three matrices here, the sum of three matrices, then, well, if we just do the same thing as Golden-Thompson did, then this is not true, it's not going to hold. But if we do something more clever, we get this Lieb's triple matrix inequality here. And you see, so this matrix H3 here, it's kind of sandwiched around the H2. And in the commutative case, one could just switch the order of those, right? And then the whole thing would just give this integral that we have below here. And you can check that this is just going to, if you integrate this thing, it's just going to give you an x again. So that means it's kind of the way this H3 is sandwiched in, it's kind of a non-commutative way of multiplying, just a very specific way, okay? And you really have to do it that way, otherwise it will not hold. And again, this is the core argument of strong sub-additivity, is this multivariate trace inequality. Okay, and so now in this talk, I just want to take this further and talk about this connection of entropy for multipartite quantum systems on the one hand and multivariate trace inequalities on the other hand, okay? So here's a short outline. I would like to develop things actually from the classical case, from the commutative Shannon entropy, and then talk about entropy inequalities and corresponding trace inequalities. Okay, and then we have some proofs. Let's see how much time we have. Okay. Okay, so let's just quickly start with the classical setting, because one can nicely develop the quantum setting from that as well. So here we have the Shannon entropy of probability distributions. Yes, I also put this Reni reference because he kind of gave an axiomatic justification why this should be the entropy function and not other functions. And then if we're interested in multipartite systems, we actually need to extend this a little bit. And as Mark also this morning nicely introduced, he talked about this parent quantity of relative entropy. And so in the classical setting, this is just this well-known Kullback and Leibler divergence, right? And then, okay, so why does this have anything to do with multipartite entropy measures? So from this relative entropy, one can just kind of produce all multipartite entropy measures that we're interested in. I have here an example. It's again this strong sub-additivity, right? So now just with x, y, z's, because we have classical systems. So this strong sub-additivity, you can actually write it as a relative entropy inequality, right? And what you see here, the C system is only on the left, but it's not on the right. So it's really kind of a neat way of writing this entropy stuff is using this relative entropy. So that's why we really have to talk about this relative entropy quantity if we want to understand what's happening. And then instead of looking at this strong sub-additivity, we can go a little bit more general, and there is this monotonicity of relative entropy, okay? So that just means that under any operation, kind of the relative entropy distance cannot go up. And this is really the kind of the fundamental mathematical property of what we know about entropy, basically. Okay, so that's just the starting point, these classical definitions. Going quite fast here, but I think people know about this. So then if we go to the quantum case, right, we also know we have the von Neumann entropy. And here, one way to think of it is, of course, we can just take the Shannon entropy of the spectral decomposition of our density operator, right? Just diagonalize it and then apply the classical definition. So that's, of course, very nice. And on the technical level, this actually simplifies a lot. Because if we want, we can just always go to this preferred basis. And then the entropy is easy to handle. We can just kind of translate classical properties. But now the next step was to go to this relative entropy. And then things become a little less clear. So one thing we could try is also to go into kind of a preferred basis, or to do like preferred measurement, and then apply the classical definition, right? So this so-called commutative relative entropy introduced by Donald. Here you would take your two density operators to start with, and then you would apply any measurement, and on the post-measurement probability distribution, you would just apply the classical Kullback-Leibler divergence definition, right? So that's a possible definition, of course. However, we can also come up with other definitions, right? And I think this relative entropy by Omegaki, Mark also had it on the board. This is this measure we know very well, I think. But here I want to kind of emphasize that there are many possible ways, right? Mark also said there are like infinitely many. So another very interesting one is this Belafkin-Stasiewski type of quantity, where we would order the operators a little differently, right? And because these are now matrices, these two expressions are a priori, they're not the same. Yeah, so there are infinitely many extensions. I put those three out here because those are kind of special, as you will see in a second. So now, of course, we would want that our non-commutative extension has nice mathematical properties, right? Otherwise, it's not really a useful measure. And so since this monotonicity, under here now not stochastic matrices, but quantum channels, which are just maps that take density operators to density operators, right? On an input system to an output system. We would still want this monotonicity because this is the main property. So this is needed to have for a useful measure. However, this also doesn't really single out anything, because actually for all those three quantities we can show this monotonicity. Okay, so now the question is, how do they compare, right? Maybe all these three definitions are the same. However, it turns out that they're actually ordered, and they're only the same in the commutative setting. So only if the states, if the density matrices commute, then these three definitions are really the same. Okay? And here, let me just say a few words about this. So one way of proving this chain of inequalities is using these variational characterizations of the entropies. And these are basically, I mean, these are just the Legendre transformations of the functionals. And what's really nice about these expressions is that the dependence on rho is split from the dependence on sigma, okay? So that is technically really, really useful in practice. Okay, and then also, for example, this measured this commutative quantity here, remember, we had to take the supremum over all possible measurements. And this is an unbounded set, right? We can have arbitrarily many measurement outcomes. Whereas this formula is a well-defined convex optimization problem. So that's kind of nice. Now for this Belafkin-Stasiewski entropy, unfortunately, there is no closed expression here for the Legendre transformation. So you see there is no supremum here. And so since there is no closed expression here in general, if we take the supremum, I just put the optimizer here, okay? So, and the reason I put this here to make the connection again is really to see now this chain of inequalities here, how they're ordered. We can now exactly apply the Golden-Thompson inequality and the complementary inequality, okay? So the Golden-Thompson says if you want to upper bound the sum here, right, you can just take the product of the individual ones. And there's also an inequality in the other direction where we have to take this matrix geometric mean of the two matrices. And basically, okay, so I'm not telling any details here because I didn't tell you what the optimizer is and so on, but basically this elementary inequality here, this allows one to prove this ordering, okay? So if anyone knows...
so Mark, you know there is big gaps between D and DB? Like between D and DK you can have, right? This.
How do you do that?
Between D and DK?
Yeah. Well, okay, I think there are arbitrarily big gaps if you look at arbitrarily big dimensions, but I cannot tell you a reference where there's a proof. But if we are very interested, I think we could establish that. Or maybe someone else knows, I don't know. Okay. Very, very good. Yeah, so these quantities are really very different in practice, I would say. Good. So now we have these three quantities, but so they're all nice, you know, but which one do we want to use now, right? And then I would argue that somewhat surprisingly, actually, it turns out that basically for anything you want to do, this Umegaki definition is the right one, okay? One can come up with different type of intuitions or precise mathematical reasons for that, but one I like particularly is because it has something what I would call a chain rule, okay? So for example, so what I mean by that is that, for example, it would generate this strong sub-additivity, okay? So this strong sub-additivity inequality, this is not generated by these other two measures, by the commutative or the Belafkin-Stasiewski one. And this type of chain rule behavior, one can also make it axiomatic in some sense, like Petz did, but this is really in every problem we encounter, we kind of want that, okay? So that's why this measure is singled out. Okay, so now finally we have established the function we want to study to understand multipartite quantum entropy. Now let's go back to this monotonicity of relative entropy, right? So this is just, again, under quantum channels, the relative entropy cannot increase, and there has been some recent development in quantum information where we looked at refinements of this inequality, okay? So the monotonicity is the most important, the most basic entropy property we have, and now to push this further, we want to look at, can we refine this in some sense? And if we look for refinement, it's good to look at the equality conditions, right? So when is this thing exactly the same? And then this theorem by Petz, it says that this relative entropy distance doesn't change under this channel n, if and only if there is an operation that reverses, okay, this noisy channel n, okay? So at least on these two inputs, rho and sigma, right? If on two given inputs, rho and sigma, the relative entropy distance does not change under a given channel, then one can reverse it here, okay? So the n of rho goes back to rho, the n of sigma goes back to sigma. And this is really very non-trivial, right? I mean, if you have one state and you want to and one channel, and you want just to reverse this channel on this fixed state, this you can always do, right? You can just do the reversal channel could just spit out the original row. But if you want to do it for the same channel at both times, this is a very non-trivial condition, right? And okay, so this operation is not unique, and but it can be chosen independent of rho. Okay, let's just say that. Okay, and now, okay, this is a bit of a heavier slide. As I already mentioned, I have this like the last 3 years or so by many authors. There have been this development where we refine this bound. Okay, so we start with the left-hand side is the same, but now we don't put a lower bound of 0, but something that is in general non-zero, and will tell us something about not the exact equality conditions, but about the approximate equality conditions. So there are these 3 bounds here. They're basically just in terms of different distance measures. Okay, so the first one is just Ullmann's fidelity. The second one is this commutative relative entropy from before, and the third one is the normal omega-key relative entropy. Right. Now, for the purpose of this talk, let me talk about the blue one here, the second one. Just explain it from there. So the first argument is just the rho, and then the second argument is this large operation here, which is actually a quantum operation applied to rho. Okay. Now let's look at this. Let's look at this operation here. So it is a quantum operation, first of all, and second of all, it's exactly this recovery channel that we had on the previous slide for the exact equality case, right? So the properties of this channel were, so first of all, if we apply it to n of sigma, it would take it back to sigma, right? And as you can see, if you can see fairly easy, if you put in n of sigma here in the middle, it actually spits out sigma again, okay? And then you have this probability function here, but this will just integrate to 1, right? Because it's actually probability distribution. So you have this, so the n of sigma is mapped back to sigma, okay? And now the interpretation, sorry?
Same kind of question, like, can we prove this to dB, or is that not?
Well, dB is larger than all the other ones.
So you get better bound, right?
Yes, but we also know that we actually, so here, we need this, already for the omega-key one, we need the the regularization, right? Which you know from a paper of Omar.
The regularized dB, yeah.
The regularized dB. I don't know, but actually I would argue that it's, if anything, it's an upper bound. Not for this relative entropy thing, but for the CQMI, for the conditional mutual information. I think, unfortunately, this might be wrong, but this would be a natural conjecture that it actually becomes an upper bound. The non-regularized one, even. Because for the conditional mutual information, right, it's an equality to the relative entropy distance. And then you go to the commutative one, which is the smaller measure. It's a lower bound. So you would hope that maybe if you go to this Belavkin-Stasievsky, it becomes an upper one. Yeah, but it's wrong, right? That's the thing. So here I say the regularization in 3 is needed. So it's wrong without the regularization. So I mean, so it's even wrong for any type of recovery channel here, not only for this particular one. Yes, so let me finish the interpretation of this. I mean, most people probably have seen this many times over the last couple of years, but let me say it anyway. So now if this thing is not exactly equal to 0, this relative entropy distance, but let's say equal or smaller than epsilon, right? This means that the right-hand side here, so let's again look at the blue one, is also smaller than epsilon. And then this means that the rho is actually closed to this recovered rho here, right? And then we already know that this R, it recovers sigma well, okay? So that means that if the relative entropy distance only changes a little bit, then we have an approximate recovery map, just this map here, okay? So it's really, yeah, it just somehow tells us like how irreversible a channel is, right? This criterion here. Okay, and so here, just for the experts, again here for the third bound, so you cannot do a lower bound without this regularization, where you just would look at the relative entropy distance of rho to the next recovered rho, even if you optimize here overall all these recovery channels and don't look at this particular one. Also, so the D, we know the D is never smaller than the commutative one, and actually we know the commutative one is never smaller than its minus log fidelity. So you might think that there's this, that these bounds are kind of ordered, but they're not. So because here this distribution is outside, and we can actually prove we cannot take this distribution outside here. So these bounds are really like three incomparable ones. So classically there's one bound, but in the non-commutative setting it kind of splits up in these three, I would argue. Okay? I mean, okay, there have been many works, right? And actually, so these bounds, the reason I listed these particular three ones, because from those, all others follow. So it's all weaker. So that's why I have these three. But so to look at this equality here is, or this inequality, and to find better lower bounds, I mean, yeah, it's just a refinement of this monotonicity of relative entropy. And maybe the next slide is better, because as a special case of this, right, we have this quantum conditional mutual information. So it's basically a refinement of strong sub-additivity, and you know, strong sub-additivity is very useful, and so that's why people wanted or started looking at this. It's kind of like a refined constraint on the multipartite entanglement structure of quantum states. So yeah, so as a special case of the last slide, maybe people know this setting better. It's about the quantum Markov chains in some sense. So here we just have the strong sub-additivity entropy terms, but now all on one side, okay? So there's just the minus now of those two. And then people call this quantum conditional mutual information. Actually, this should be probably an A, B, C here. I'm not wrong. But now if we, okay, so it's easy to see that we can apply the other setting, and then we get this lower bound, right? Before, the strong sub-additivity was just a lower bound of 0. Now we have this refined bound. And so why is this related to Markov chains? Well, so the interpretation here is that you can build up the global state on ABC by taking the AB marginal here, right? Just this AB marginal, and then only acting on B to create C, right? So you can kind of iteratively build up your state in some sense. So that's the type of Markov structure that survives in this quantum setting, if you want. Okay, so the first version of this was proven by Omar and Renato, and then there was this whole development. And here I'd like to argue that you know, you can do all these operational nice proofs, but if you want the tight bounds, kind of, you really need to understand the matrix analysis behind it. So you really need these multivariate trace inequalities to get all these tight bounds and to have the full understanding of what's actually happening. Okay, so for now, let's not look at this monotonicity of relative entropy anymore, but focus on the strong sub-additivity special case, because it's a little bit simpler. So now let's go back to the original proof, right? On the very first slides, the motivational slides, I told you that this strong sub-additivity followed from Lieb's triple matrix inequality, but I actually didn't tell you why or how, right? Now here, let's do it. Now it's kind of a short proof now. So these conditional mutual information, which you remember are just all these entropy terms from the strong sub-additivity. So we want to prove this is never smaller than 0. So the first step is we can write this as a relative entropy distance. So here you can really just write it out, okay? If you look at the definition of this omega k relative entropy, it has a logarithm in there, and this logarithm kills this exponential here, and then it just plays out right, okay? And then the first step is you can derive with Klein's inequality. This just means that you can lower bound the relative entropy by the difference of the traces of the argument. This is pretty elementary, but I'm not going to go into more details here. That's the first step. And now you see, once you did that, and again, it's pretty elementary, all you need to show is that this exponential operator is subnormalized, because then you have a lower bound of 0. And this is exactly what this Lieb's triple matrix inequality does. So now I've wrote it with a log m1 in the exponent. But I mean, you could just set this log m1 to be like a P1, right, another matrix, and then it's the same inequality as on the second slide. So you have this upper bound here. Now you apply it. So for M1, you choose row AB. For M2, you choose row B to the -1. And So the minus here, I mean, it's an inverse, so if you have full support, it's fine, otherwise you have to be a bit careful. But then you have the M3, you choose as rho BC. Of course, all these operators act on the full system ABC. So what I didn't do is, I didn't put the identities, okay? So here there would be a tensor identity C, here there would be a tensor identity AC, and so on, right? It's kind of implicit. So now if you do that, then you can use that this is a full trace, but the trace you can split up in partial traces over all the systems that you want to trace out, which here are ABC, and then the partial trace commutes with the identity, okay? So that means the partial trace over C, we can actually take inside M1 here, right? Because this one has an identity on C. And then once we have the partial trace in here, we can, the M3, right? We can actually take it even further in to the M3, and then for here we can take the partial trace over C, so all that survives here is a rho B. And this rho B in the middle, it commutes with the rho B minus 1, because, you know, they're diagonal in the same basis, and then this whole thing here, it collapses, right? Actually, this should be, we have an X here. Okay, so now I'm a bit confused. This is the right integral. But the point is that this whole thing collapses to an identity, basically, and then it collapses to a row C, and then this one only, collapse to an identity, and then you have the row AB left, sorry. Yeah. Anyway, so you get an upper bound of 1, right? You see, sorry, what I'm talking about. And then this is the proof, right? So it's really this argument, this Lieb's triple matrix inequality is really at the core of the argument. Okay, so that was the proof of strong sub-additivity. Now we want to do this tighter bound. So I propose to do the following. So the first step is the same. We're going to write this condition mutual information as a relative entropy distance. But then we don't use Klein's inequality because, I mean, maybe not too surprisingly, then we would already lose too much. So, but we use this variational formula. You remember I had this variational characterization on the screen before. And now you see the second term here becomes an exponential of 4 operators. So the fourth one is just this omega ABC that we optimize over. And so to do anything with that, we don't need this 3 matrix Golden-Thompson, but we kind of need a 4 matrix Golden-Thompson. Okay, now of course the whole point of this talk is that we have this now. I gave you this Golden-Thompson just for the trace here, okay? But you can actually extend it to any unitarily invariant norm. And this theorem here is the extension of the Golden-Thompson inequality to arbitrarily many matrices. Right? So here on the left-hand side, you really have the exp of the sum of all these single matrices, and then on the right-hand side, you have the product of the exponentials. Right? Of course, it's not just this kind of simple upper bound, but there is this phase here where we have to rotate things a little bit. This beta 0 is, again, it's a probability distribution. Okay? Now, of course, you ask, yeah, okay, but you know, we had this Lieb triple matrix inequality, right? So this looks different. So what's the connection here? So if you want to look at this Lieb triple matrix inequality, so you, of course, you choose n equal to 3 because you had 3 matrices. And then if you don't look at a general unitarily invariant norm, but the 2 norm, the Schatten 2 norm, and then you, to get rid of these logarithms, you can use Jensen's inequality, and then you actually get this expression. And it turns out that this expression is exactly equal to this bound that we saw by Lieb. Okay? So in retrospect, what you can think is that this form of Lieb, you have to rewrite it in this complex form with these phase rotations, and then it naturally generalizes to n matrices, where this form, at least a priori, doesn't generalize to more than 2 matrices. Okay? Okay, so now to prove this, we actually first show something more general, which is an extension of the so-called Araki-Lieb-Thirring inequality. So there's this Lie-Trotter expansion, right? So if you have the exp of a sum of logs here, then we can actually write this as a limit. If we take the powers of the individual matrices, multiply all with them, and then take this global power of 1 over R. Okay, this well-known Lie-Trotter expansion just for n matrices now. And now instead of having this Golden-Thompson for the exponential function, we can actually show this more general thing where we look at these power functions. Okay? So on the left-hand side, here we take the individual matrices to the power of r, and then a global power of 1 over r. Whereas on the right-hand side, we put this global power on each individual matrix, right? So it's kind of the same thing as for the Golden-Thompson, where we have like this global function, and we want to apply it to each one individually. But now here it's just not the exponential function, but this power function. And this is really strictly more general, because we can actually take this Lee-Trotter limit and then get the Golden-Thompson again. And you know, you can play around with this a little more, and then you can also show multivariate extensions of other trace inequalities. So one that is very related is, for example, this one, which is the two-matrix form for only two M matrices is due to Hirche and Petz. But you can actually extend this now. So you can again have these N matrices over here. But anyway, let's not go more into this direction where we just take arbitrary trace inequalities and try to make them multivariate. But let's really look at how one can prove this. Now, the strongest kind of proof technique here is via complex interpolation theory. And as far as I know, this was first used by Epstein in '73. And then in this particular form, this strong form that we will use it here by Kosaki in '97. And then in quantum information, there has been kind of a revival of these techniques, and especially these later three papers where Mark was kind of proposing this technique in some sense. They were using this also for looking at entropy inequalities directly. Okay, so the core thing here that we use is a strong version of the Hadamard three-line theorem, right? So there are lots of technical conditions here, but basically you look at a holomorph function on the unit strip, okay? And then the theorem just tells you, if you have this holomorphic function, if you want to control the value of this function on the real line, you only need to look at the boundary of your strip, right? So you only need to look at it and 1 plus it. Okay, and now the normal Hadamard three-line theorem is this second inequality here, where you just say you only need to look at the maximal value on the left-hand side of your strip and the maximal value on the right-hand side of your strip. But this is a stronger version due to Hirschman, where if you look at a certain probability distribution on the boundary of your strip, actually you can have these stronger bounds. Okay. Now, of course, this is for scalar functions, so we need a version of this for matrix valued functions. And one case where it becomes particularly simple is for the operator norm. Okay, so now just you have an operator valued function here now, but instead of the absolute value, we take the operator norm. And then it's very easy to see that you can lift this from this small g to the capital G here. Again, you can just do this by defining this function small g. So you apply this theorem for this function small g, and then you get this blue inequality. Okay, so you fix r, and then of course you can write the operator norm of g of r in this way, you know, where you just take these u and v's where it's attained, and then for this fixed r you can define this function g of c, okay, where this u and v are the one from here, okay, for this fixed r. And then the left-hand side, of course, it just becomes equal, right? Because here you look at g of r, so it's really the same thing now. And on the right-hand side, you can just upper bound these absolute values here, elementary, by the operator norm now of g of c. Okay? So it's very, very simple, really, here, the operator norm. Okay? So now let's use this, and now let's not prove it for arbitrarily unitary invariant norms, but for this operator norm. Okay, we proved this multivariate Araki-Lieb-Thirring for the operator norm. So that's how the statement looks like that we want to prove, right? And so it's really a two-line proof now, basically. So you want to apply this Stein-Hirschman theorem. Okay, it's just the same theorem as on the last slide. But now we apply it to this function. Okay, we just take the product of the matrices to the power of c. Okay, so this one can check that this function actually fulfills the conditions of a Hirschman theorem. And if you plug this in, so what happens, okay? So first of all, this term here becomes 0, right? Because if you take this m to a power of it, these are just unitaries. So they will have largest eigenvalue equal to 1, and log of 1 is 0. So this term will just disappear. And then the second term here on the right, it will be exactly this term that we want, except for the power r, the global power r, okay? But the left-hand side will also exactly be the term that we want, but here up to this power of 1 over r, okay? But those two we can just cancel out. Again, because we are in the operator norm, of course. So that's really like the simple case where you can see kind of the core argument and how to prove this. And you can extend this a little bit, not too much, but then you can get the general theorem, okay? The general multivariate Araki-Lieb-Thirring for unitarily invariant norms. And you can then, again, use the Lie-Trotter expansion to go to the Golden-Thompson, okay? Good. So now I proved these multivariate trace inequalities. Let's go back to the entropy thing, right? So I said, you know, we need a 4-matrix Golden-Thompson to prove our refined entropy inequalities. So let's do this now, okay? So we need 4, so let's put n equal to 4. And now let's put the norm to 2 norm again. We proved the operator norm, but I also mentioned that, you know, with like some easy additional steps, you can also get the 2 norm, okay? And so then the upper bound looks like that, okay? So now we just have to plug it in, and it's basically there, okay? So we start with the conditional mutual summation again, equal to this relative entropy distance. We had this on the screen before, right? And then I said we use this variational expression. So that's what we had before. So we had this 4 matrix exponential here. And now, of course, you know, we just choose M1 to be omega ABC, M2 to be rho BC, and so on, right? We just choose the right ones. I mean, this minus here, we just put it inside here on the rho B. So let's just choose the right operators. And then if you apply this blue expression here becomes this blue expression, right? It's really just plugging it in. And now, there's this other variational formula for the commutative relative entropy that I had on the board many slides ago. So what we can see is now that this whole expression here, when we again optimize now over all omegas, is actually equal to this commutative relative entropy. Actually, this should be an equality here, I think. Or yes. So this is really exactly what we wanted to prove, okay? So the last line here for forget about it, it's just an abbreviation, so there's nothing happening here. So this is exactly this recovery map from before, right? Where we claimed that we can build up this state rho AB by only acting on B, okay? So this is really the statement we set out to prove. Okay, any questions here? Yes, please.
So probably the inequality comes from the fact that you bring this eta 0 inside the log, right?
True, yes, of course, yes. Thank you. Yeah, so I thought about something when I made the slides. Thanks. Okay, good. Yes, so let me just mention here that now all these other bounds, you remember there was another bound in terms of the fidelity, there was another bound in terms of the relative entropy distance. There were more bounds for this monotonicity of relative entropy and not just strong sub-additivity. They all follow similarly, okay? It's always the core step is this 4-matrix Golden-Thompson. Okay, so that's pretty much what I wanted to say. So let's have a conclusion or / outlook. So what I showed you is some strengthened entropy inequalities. And I try to argue that this is kind of in a one-to-one correspondence to multivariate trace inequalities. Okay, so if you want to understand entropy for multipartite systems, you need multivariate trace inequalities and vice versa. And the technique we used was complex interpolation theory. Now, of course, you can try to ask, like, okay, where do you go with this? So one interesting point that was discussed a little bit about literature is that we had this integral, right, with this beta 0 probability distribution. And what Lieb's original inequality was in terms of this lambda integral, in terms of these resolvents, right? And recently, Marius Lem showed that one can also write these multivariate trace inequalities in terms of this lambda integral, in terms of these resolvents. And even more recently, there was this new kind of representation of this integral, where these authors at least claim it's very useful that it's now on a finite interval that we only have to integrate over. Okay, so at least myself, I don't really have a good understanding like about these different representations. So I think that's an interesting direction to go, because different representations have different kind of properties and that are useful in practice. Okay, and then of course you know, we can ask like more generally multivariate matrix analysis, right? Now we can take like any trace inequality we want and we can try to make it multivariate. And there has been some development in the mathematical physics literature. And so one interesting problem I think is this complementary Golden-Thompson inequality here, for example, we don't have a version for more than 2 matrices, or at least not a closed expression version. Yeah, and of course, maybe you're not necessarily interested in matrix analysis itself, but actually in entropy. And then there are many quantum entropy inequalities that we would like to prove. And some of them are the so-called non-Shannon type information inequalities. But there are many other interesting conjectures. So if you're interested, you can also talk to me later that we would like to be able to prove using these multivariate trace inequalities. And then, so I didn't really mention this, but there are lots of references about applications of these kind of refined bounds. And again, I would argue this is because this now gives you a refined constraint on the structure of multipartite entanglement. And yeah, this is in general very hard to understand. Okay, thanks for your attention. That's all.